Greetings. In this one, I'll be working with something related to statics, the static equilibrium of a rigid body, and I will be calculating support forces and reaction forces of the supports here using equations of equilibrium, which take into account the statics approach. We know that the x direction forces are summing up to 0. The y direction forces are also cancelling out each other all in total when summed to 0, and moments at any point, the sum of all moments on that rigid body at any point of it, or any point in general, is going to be 0. So with that approach, we're gonna solve this problem. And the solution to this problem, what it really means is, well, we are considering this sort of object. Let's say the height here is 0, just for simplicity. We're only going to be considering distances horizontally. We won't consider vertical distance hereby. If I say that this straight rigid object, let's say a plank or whatever it is, has a 0 height or a negligible height, so that we will only consider the width, and so, or the length, like this. That will simplify the calculations and make it easier to understand, especially with this example that one is supposed to understand it with. And what we will now proceed to doing is, we will first identify what reaction forces we're actually looking for. So we are faced with a body that has some forces already written out. We see also distances. We see that 2 meters from the left, this is, let's say this distance is the 2 meters, this running is the 8 meters, in total it's 10. Here on the bottom there's a force that divides it into 2 equal lengths, 5 and 5, so the total length of the object is 10 meters, whatever it is. Not necessarily important for this example. And there's already 2 forces explicitly shown. First of them is this force that kind of pulls it up to the top left side under an angle of 45 degrees from the x-axis. The smaller angle is 45, the other angle is 135, but it's just a side note, not important, at a magnitude of 20 newtons. So 20 newtons pulling in this direction. Now, we will break this out into the y component and x component, as we can always do when we have our imaginary x-axis and y-axis. That's basically present. We can always refer back to that, especially when we have object oriented in such a way that we really see that it's positioned in the x direction, and in the y direction we have at least one of the forces, and then the other one we can break out. And then because it's positioned like this, we have these reaction forces here. This will also be either perpendicular or parallel to x-axis. Therefore, yes, let's just focus on this through the x-axis and y-axis as standard, being like this, x-axis and y-axis like this. It's going to help us with calculations and everything. So this b will be broken out into b sub x, b sub y, being the y component and the x component of the same force. It will be an equivalent expression via 2 forces that are perpendicular to each other. It will replace that single force in this arbitrary angle, or we see concretely 45 degrees. Then we have this weight force that's pulling the object down. It's applied at this point. That's a simplification matter, and it is very often so that diagrams like this, they count with the weight force basically as a force arrow, as a force vector, but the point where it has to be somewhere, where it lays or where it starts has to be somewhere, so we just say it's in the middle. It's a symmetric object, so let's say the weight force is in the middle, applied here at a magnitude of 100 newtons. And now, to proceed with the calculation, or to actually start the calculation, to proceed with this process of solving it, we have to perhaps draw a free body diagram that will only tell us what we're looking for, what we have, even in a more simple manner. This has already been simple, but there are some things that one might not know yet. We might go into this more concretely in another one, presenting more types of concrete symbols of, or let's say we might at the very least run into these kinds of symbols more in other videos, perhaps more of such symbols, or there are alternative visual representations. But what they mean, these 2 symbols, are basically behind them are hidden some forces, just like we see here. Behind these 2 things are hidden some forces. They are called supports, and based on how many forces they hide, plus how many moments they create, how many forces they act as. Then we will say 1 value support, 2 value support, 3 value support, and so on, based on how many directions, how many degrees of freedom such supports affect. What these supports basically mean in real life is some devices that hold the thing in place. Because it is statics, it is held in place. The thing does not move, and that's the basis of our calculation. So first, now let's do the free body diagram. We will, as I said, consider this as 0 height, just the length, the total length being 10 meters. At one side we have this point A. Then after 2 meters, so there's 2 meters elapsed, then we have this 45-degree angle for this force B equaling 20 newtons. Of course, the y and x components will have individual values, but that's another point. Then we have the remaining 8 meters. In the middle of the thing, we have 100 newtons down, straight down, vertically straight down. And on the right side, we have point C. Now, these two things will be replaced by more forces. When we have such a symbol, it means that there is a support in the vertical direction and that it can slide like this. It means it's held such that it doesn't go up and down, but it's not held horizontally. This is this symbol. What that means in practice is that we're going to be looking for some force A, let's say AY. We have no other than AY here, just AY. I could just call it A, possibly, but to make it more systematic, because there will be two forces here, by the way. So to distinguish it, so AY, and it will equal to something, and that's what you're looking for. So that's one of the results that our calculation is looking for the whole time now. So this thing has been replaced by this. We know that this represents a support that supports it vertically, and so we can draw one force AY. We will look for the magnitude, and I also guess the direction. I guess the direction is going to be up, but in case it is not, our calculation will work still. Doesn't matter. We will do the calculation the same way. The only thing that will change is if the magnitude of us calculating with this direction will turn out negative. It means that it is this direction negatively, or in other words, we switch the arrow pointing down instead of up. That's the usual practice, and it's how it works. When we guess the opposite direction and it ends up as minus, it's the same thing like if we guess the other direction and it ended up as plus as a value of that force. Now let's proceed to the right point. So these are the last two forces, actually. Behind this are hidden the last two forces we have to identify before starting the calculation and establishing the equilibrium equations and so on. So behind this point, it's called point C, as you see. This is actually an example of a support that supports the body in the way that it does not stop rotation, some possible rotation, but it blocks it from moving to the left and right, horizontally and vertically. So there's going to be both a support force vertically, let's say C sub y, and force horizontally, let's say C sub x. And why I guess it to the right is because the only other horizontal thing is going to be the horizontal component of B, and that one is going to go to the left. So to have an equilibrium later, we will need something to the right, and this is the only thing that seems to be actually repelling that effect. So perhaps this will be correct. This is quite expectable to be correct. Now 8 is meant as the remaining thing from here, so maybe better to again show this whole thing is 8 meters, this was 2, and then we have 5 and 5 like this. Alright, so this is our free body diagram here. We have, this is basically the object, it's like a straight line thing, and there are some forces acting on it. And using equilibrium equations, we'll be able to determine these three forces, AY, CY, CX. So how do we do this? Well, there's more ways we can approach it. The most often used set of equilibrium equations are an equation involving the sum of moments around a particular chosen point, then sum of x forces and y forces. So I can write it out. What we expect, because it's a static system, and that's the idea of how we're solving this, is we have f of f sub x, those are x forces, and this something means that it's all forces in the x direction on our free body diagram have to sum up to 0. That means the left and right that repel each other will together make up a 0. Those that go to the left usually seen as minus forces, those going to the right usually seen as positive forces. The same analogy applies for vertical direction. It means up is going to be plus usually, down is going to be minus. So I can also denote it in this notation. I can put an arrow up and show that I mean plus by that, or I'll just leave it and let's just say we use the more common way now in this case. With moments there's also more common choice, but it might depend on the example what one chooses. If one solves a hard example, one might actually choose the opposite direction and denote it in that equation somewhere here, because it might be more practical for him, but that depends on the concrete example. In this case, let's just stick with the defaults. So we see we have all forces in the x direction equal to 0. And what we do here is we use this fact and we actually write out what the x direction forces are, and that will give us an equation for actually calculating their values. So the idea here is that we identify x forces. Well, to identify them, it's very useful to break out forces that are not perpendicular x and y directions completely, and break them out into x, y components. The only force that's not so is this one, the b. So to break it out, we have by. So basically b will be represented by by and bx, just like here is, so b will be the same. So then we have bx. I'll draw it like below here because this line is not so small. We might have problems seeing it. So yes, because it has this direction, I will do bx to this direction and by to this direction. It follows the thing. Alright, and bx and by will be directly derived from the value of b, which is 20 newtons, just multiplying by knowing this angle, 45 degrees, and using some trig functions. So these trigonometric functions are as follows. If we want to calculate by, it's going to be b, and this, when we are looking for a y component of a force, then we're looking for b for that force times sine of the angle that it makes with x-axis 45 degrees here. Then if we look for the horizontal component, the x component, we do the force times the cosine of that angle. Now in this case 45 degrees is the same value for both sine of 45 and cosine 45 are the same actually. So in both cases it's square root of 2 over 2. We won't use a calculator and enumerate it as a numerical approximation, although it is very often done, and it's probably the more common practice in statics. But we'll just stick with the exact values of the roots, just not to have to use calculator now, but of course you can do it if you want. So b times sine of 45 degrees is going to be this 20 times sine of 45 degrees. So 20 times square root of 2 over 2, that means 10 square roots of 2. Then this is going to be the same because we know that cosine of 45 is the same. So these two results actually end up the same. And it's also logical, we see the angle is going up vertically, same like it's going horizontally. Therefore, the x component and the y component should be the same length, which they turn out to be. So yes, bx is going to be equal to 10 square roots of 2, and this is also 10 square roots of 2. Newtons in both cases. We could also put newtons here, but we were just working with the numbers here, so let's say that. That's it. And so we have figured out a few things here. We just took this b and analyzed it and showed the values for the two components that are equivalent to it. And so now we can start writing out this first equilibrium equation. So the first, as I said, is the forces in the x direction. So which we have? Well, we have bx now here. We got it to the left. So that means we will write it out. Its value straight away we can do, or just write the letters first. So it's bx, but because it's to the left side, we will say it's minus bx. And then we keep looking. There's nothing other in the horizontal direction until cx. And then it's to the right, so I'll say plus cx. Now we can identify minus bx is minus 10 square root of 2 newtons plus cx. And this implies that cx is actually going to be the same magnitude, and cx is going to be 10 times square root of 2 newtons. So we got the result for cx by this. This was quite quick. So we have that. The next one we can use is perhaps we can work with we can look for the y forces. So Fy is going to be 0, is going to be, now what it is? Well, we have Ay going up, By going up, this going down, and this going up. So we have Ay plus By, both going up, so both plus, minus 100 going down, that's the weight, that's the minus Vw. Here, I already wrote the number, but we could have also just first written the letter, so it could be universal. Then Cy is also up. Alright, so we have that. And here we are actually getting into a little bit of a trouble, because yes, we have By, but both Cy and Ay we don't have at the same time. So yes, we can at the very least write Ay plus By equals 100 minus Cy, if we write it. And that's going to be 100 minus C sub y is in another way, we want the unknowns on one side. So actually we will have Ay plus Cy equals 100 minus the By, because we know By. So it's 100 minus 10 times square root of 2. So now that we have this, this is actually getting us a little closer, but still we have a problem. We have two unknowns and just one equation here. So that means we will also need to use the third equation of equilibrium. And in this case, we're not going to be talking about the sum of x forces or y forces equaling to 0. We're going to be talking about all moments for a particular point, summed up, equaling to 0. That means you will choose one point and get the moments for that. So which point could we actually choose for this? Well, it could be quite practical to choose, it depends on one's choice, but actually it could be quite useful to perhaps just choose one of the edges, because when we take a moment at a point through which we have an unknown force, that unknown force doesn't have to be used for that moment, so it won't be in the equation and we can actually solve. So let's say we will take the moment about C. So let's say, or maybe we could do also about A. Let's do a moment about A in this case. So if we do the moment about A, we do this equilibrium equation again, the same idea again. And what we do is, I'll write it here, just like we did all x forces, all y forces, we will have moment sub A. And the usual way we talked about moments as positive are the ones that go anti-clockwise. Those are positive, and those that go clockwise are negative. So when we are seeing that a moment for that point is anti-clockwise, it will be counted as plus, and minus in the opposite case. So all moments at A, so all moments for this point, for this whole free body diagram will be 0. And what will they equal? Well, at A we have Ay, but it goes through the point, so it's not a moment. It doesn't cause a moment. When the force goes straight through a point, it's not causing it a moment. When its action line goes to that point, it's not causing that point a moment. Then we have Bx. It's also going straight through it, but By does not. And how far is By? Well, now we see By is 10 times square root of 2, and it is 2 meters away, and it's actually going anti-clockwise, so it's actually going to be positive. So we have By times 2. I could have used the 10 times square root of 2. I'm going to do that in the second step just to make it simpler first. So By times 2, we have it like this. Then we have 100 times, how far is it? This is 5 meters. It's the half as we had here. So This is actually going to take it clockwise, therefore it's negative, so minus 100 times 5. There's the W, again we're running the numbers straight away. And then Cx, again, actual line goes through A, but Cy not. So we are actually getting Cy here, using just By in this equation. That's the point of it. So yes, Cy is actually 10 meters, the whole 10 meters away, and it's taking it anti-clockwise, so it's positive. So it's Cy times 10. Times 10. So from this, I can also directly express Cy. So Cy, just equaling this to 0, right? So Cy will equal to 500 minus 2 times By. That's 20 times square root of 2. And we will divide all of that by 10. So it's going to be 50 minus 2 square roots of 2. And so now that we have this, we directly expressed in, and this is going to be in Newton, by the way, Cy. So now we see from this, it's 50 minus square root of 2 square roots of 2 newtons. So because we're not enumerating it as numerical approximation using a calculator, we will get these results with square roots, but this is still a single number. And if you want, you can of course evaluate it with a calculator as numerical approximation. So we see 50 minus 2 square roots of 2 newtons is the value for Cy. And now the last thing we have to get is value for Ay, the last one we're missing. What is going to be equal to? We can go back to the equation that we could not use before. F of x we fully used, f of y we could not, therefore we jump to m sum a, the moments around a, but now we can go to the sum of y forces. So we had ay plus cy equals this. Well, now we have cy as well, so we can directly calculate ay. So from this, I'll rewrite the equation once again, just for ay to be on one side. So we know ay is now going to be equal to 100 minus 10 times square root of 2, but also minus cy. And cy is this, so minus 50 minus 2 square root of 2. So what is that? 50 minus cy. Actually, this is going to be plus because there was minus here, so it's plus 2 square roots of 2. So this is 50 minus 8 square roots of 2. Just to check it. Yes. And of course, this is in newtons again. So yeah, we didn't use the units on the left side, so let's just leave it, but here we write it right with the units. So ay is going to be equal to 50 minus 8 square roots of 2 newtons. So now we figured it out all, basically. To just go back and see what we actually did in this example, we were given this diagram about this situation. We have this straight, rigid body, negligible height, but this length of 10 meters. We see the lengths of the parts. We see these forces that exist here. And thanks to using the equilibrium equations, we were able to get the values of the reaction forces at the two supports, at both the ay for the support at A, and also the cy and cx for the support of two forces at the point C.